Hello, Math 122. In this video, we'll be talking about section 5.3, which is a continuation of our discussion of the definite integral. And in particular, we'll be looking at the definite integral and how it represents the area between a function and the x-axis. So in the past two sections, we've only looked at functions that are always positive over the intervals that we've been looking at. And recall, we have this result about positive functions. So if we have this function f of t, and that function is positive over the entire interval from a to b, then we get to say the following thing about the definite integral. The area that's under the graph of our function f between the points a and b is equal to the definite integral from a to b of f of t dt. So as a picture, what's going on here, we have our function f of t and it's positive, which means that it's always above the x-axis. We have our two endpoints of the interval, t equals a and t equals b. And in this case, we can say that the definite integral from a to b of f of t dt is equal to this red area that's sitting underneath the curve, between the curve and the x-axis, or the t-axis in this case. But we should ask the question, how do we interpret this definite integral from a to b of f of t when f of t is not always positive between t equals a and t equals b? So for example, let's say that my new function f of t is this blue function, and at parts of this function, f of t is going to be above the x-axis, but at other parts, like in the middle here, f of t is going to be below the x-axis. So we should ask the question, does the definite integral from a to b of f of t still give us the area under the curve, or does it give us something else? Does it give the area between the curve and the x-axis instead, or does it do something entirely different? So this is the topic that I want to talk about for the rest of the video. In this next section, we'll talk about the relationship between the definite integral and area, specifically in the case where f of x is negative. So remember from the last video that the definite integral from a to b of the function f of t is defined to be a limit, and in particular it's the limit of the Riemann sums, which we defined in the last video, and these are sums of this form. So we have the sum from I equals 1 to n of f of t sub I times delta t, where f of t sub I is the function evaluated at the endpoints of the subintervals that we're using, and delta t is the length of each of these subintervals, and n represents the number of rectangles. So we said last time that if we calculate these Riemann sums and we let the number of rectangles that we use go off to infinity, so we keep using more and more, then we're going to define whatever that value the Riemann sums approach to be the definite integral from a to b of f of t. So if we want to figure out what happens to the definite integral when the function is not positive, when it's negative instead, we should ask the question, what happens to these Riemann sums when f of t is negative as opposed to positive? And whatever happens to those Riemann sums is going to tell us what happens to the definite integral, since the Riemann sums are involved in the definition. All right, so maybe we should calculate an example to get a feel of what happens when f of t is negative. So let's let the function f of x be equal to x squared minus 4. And the first thing we're going to do is take f of x and graph it. So in this case, we have a parabola, but it's shifted down 4 units. And so we end up with a parabola that looks something like this. And we want to calculate a left-hand sum from x equals negative 2, which is right here, to x equals positive 2, where the length of each subinterval is going to be equal to 1. Okay, so the left-hand sum is going to be equal to f of negative 2 times 1 plus f of negative 1 times 1 plus f of 0 times 1 plus f of 1 times 1. So we're breaking up this interval from negative 2 to 2 into subintervals of length 1, and then we're calculating the appropriate Riemann sum, which is the left-hand sum in this case. And now I'm going to go back through all of this function notation that I have and replace it. So f of negative 2 is going to give me a 0. So I get a 0. F of negative 1 is going to give me a minus 3. F of 0 is going to give me a minus 4. And f of 1 is going to again give me a minus 3. And if I add these things together, I end up with negative 10. So in this case, the left-hand sum gives me a negative 10. The important thing to note here is that this left-hand sum is approximating the area between our curve and the x-axis between x equals negative 2 and x equals 2. And in this case, the left-hand sum is giving us a negative value. So somehow, when our function becomes negative, the left-hand sums, or the Riemann sums, also become negative, and this is going to tell us what happens to the definite integral. So again, the key idea of this previous example is that when our function f of t is negative, the corresponding Riemann sum is also negative. And why is this happening? It's because all of these values, f of t sub I, are now going to be negative because the function is negative. And if we look at the Riemann sum, that means that all of these terms that are showing up, the f of t sub I times delta t, those are going to be negative as well. And if we add up a bunch of negative things, well, then we're going to get something negative. So when our function f of t is negative, the corresponding terms of the Riemann sum are going to take away from the sum, as opposed to contributing to the Riemann sum. So here's the key idea to take away. When f of t is negative, the Riemann sums are still going to approximate the area between f of t and the x-axis, but in this case, the area is going to be negative as opposed to positive. So if the function is positive at some parts and negative at other parts, then the positive parts of the function are going to contribute positive terms to the Riemann sum. The negative parts of the function will contribute negative terms to the Riemann sum. And in some cases, they're going to end up canceling each other. So we'll think about that a little bit more in some following examples. So the next example, what's the relationship between the parabola y equals x squared minus 1 and the x-axis and the following two definite integrals? So I have the integral from 1 to 2 of x squared minus 1, and I have the integral from negative 1 to 1 of x squared minus 1. So the first thing I want to do is take that function y equals x squared minus 1 and graph it. And in this case, we have the parabola y equals x squared, but it's just shifted down 1. And so I have my graph drawn here. This should be sufficient for us to understand what's going on. So notice that the parabola is crossing the x-axis at x equals negative 1 and at x equals 1. Okay, so for this first definite integral, we're looking at the interval between 1 and 2, and if we go up to our curve, notice that between x equals 1 and x equals 2, our function, x squared minus 1, is always positive, which means we can say this integral from 1 to 2 of x squared minus 1 dx represents the area under the curve from x equals 1 to x equals 2. So in this first case, this is something that we would have seen in a previous section, because on that interval from 1 to 2, our function x squared minus 1 is just positive. So the definite integral has the same meaning it had before. It's just the area under the curve. All right, so for part B, now we're looking at the integral from negative 1 to 1 of x squared minus 1 dx. Yes? Okay, so in this case, our function is not going to be positive. Our function is actually negative over that entire area there. So the integral from negative 1 to 1 of x squared minus 1 dx represents the negative area between the curve and the x-axis. So we can also use a calculator to evaluate both of these definite integrals. So I went over to Desmos so that I can calculate both of these integrals for you. So the first one, we have the integral from 1 to 2 of x squared minus 1 dx. And Desmos tells me that this gives me a 1.3 about, which is what I expected. Remember, I expected this integral to be positive. And now let's look at the integral from negative 1 to 1 of x squared minus 1 dx. And notice in this case we get a negative 1.3. And again, this is expected because this second integral was represented by the area between the function and the x-axis while the function was negative. So coming back to OneNote, let's write down these results. We have, using a calculator, that the integral from 1 to 2 of x squared minus 1 dx was equal to 1.33 is equal to the area under curve from x equals 1 to x equals 2, and the integral from negative 1 to 1 of x squared minus 1 dx was equal to negative 1.33, which is equal to the negative area under curve, or maybe I should write between curve and x-axis from x equals negative 1 to x equals 1. In this next section, let's start with another key idea. So when f of x is positive for some x values and negative for others, then the definite integral from a to b of f of x is the sum of the areas above the x-axis counted positively and the areas below the x-axis counted negatively. So maybe it's better to represent what this key idea is saying with a picture. So let's say that we have this function f of t in blue graphed on our coordinate plane here, and we have our endpoints t equals a and t equals b. Okay, so we're going to let this area from t equals a to this point right here, we're going to call that a1, and we're going to call the area from that point to the next point a2, and then from that point to t equals b, we'll call that a3. And in this case, the definite integral over the entire interval from t equals a to t equals b is going to be equal to the first area coming from over here minus the second area, which is now going to be taken away, and a3, which is going to be positive because it's area above the x-axis. So whenever we have area below the x-axis, we subtract it to get the definite integral, and when it's above the x-axis, we add it when calculating the definite integral. Alright, so another important fact you should know about definite integrals, we can split up integrals by splitting up the limits of integration. So suppose that we have three numbers, a, b, and c, where a is less than b and b is less than c. Then we can do the following with a definite integral. So say we have the definite integral from a all the way to c of the function f of t. Then this integral is actually equal to the sum of two other integrals that we get by splitting up the limits of integration. So we can go from a to b and take the integral of f of t, and then add the integral from b to c of f of t, and this is going to give us the same thing. So the key idea here is that we can split up the limits of integration of definite integrals into the sum of a bunch of smaller definite integrals. Okay, so in this next example, we want to interpret the definite integral from 0 to 4 of this function x cubed minus 7x squared plus 11x dx in terms of areas. So I'm going to start by drawing a graph of the function that we have here. So we have f of x equals x cubed minus 7x squared plus 11x. And so our graph looks something like this. And I'll take this graph and I'll send it back over to OneNote. So I now have a sketch of the graph of the function f of x. And you can see that I've labeled the area above the x-axis as a sub 1 and the area below the x-axis at a sub 2. And I made special note of this point where we travel over from the function being positive to the function being negative. It's going to be important for us to figure out the value of that point. All right, so that's the first thing we're going to do. We find the x value where f of x is equal to 0. So this point that I have circled in red, so that we know where to start counting our area as negative as opposed to positive. Okay, so f of x is equal to x cubed minus 7x squared plus 11x, and we're setting it equal to 0 so we can find that point. And the first thing I notice is that I can take an x and factor it out and get x squared minus 7x plus 11 is equal to 0. And unfortunately, this quadratic, x squared minus 7x plus 11, does not factor well, so we're going to have to use the quadratic formula. So then use the quadratic formula, and we're going to get solutions. X is equal to 7 plus or minus a radical 49 minus 44 all over 2 times a, which is just 2 in this case. And if you put this into a calculator, you're going to find that this point we're looking at, represented by the red circle where the function crosses the x-axis, is going to be 7 minus the square root of 5 over 2, which is approximately 2.38. So if you want to verify that I actually did the calculation correctly, then just pause the video for a second, plug it into a calculator, make sure that I used the quadratic formula properly. But once I find this x value where f of x crosses the x-axis, now I can use that property that we just found about definite integrals to split up the integral from 0 to 4. So we can split the definite integral so that we get an integral from 0 to 4 of x cubed minus 7x squared plus 11x dx is equal to the integral from 0 to 2.38 x cubed minus 7x squared plus 11x dx plus the integral from 2.38 to 4 of x cubed minus 7x squared plus 11x dx. So the reason that finding that point was so important is because it allows us to figure out when we're going to start counting the area as negative as opposed to positive. Okay, so this integral from 0 to 2.38 of x cubed minus 7x squared plus 11x dx is equal to the area of A1 in the picture. So remember, A1 was this area from x equals 0 to x equals 2.38, which we just found out. And in this case, that area is going to be positive. And this integral from 2.38 to 4 of x cubed minus 7x squared plus 11x dx is the negative area of A2 in the picture. So again, A2 was this area from x equals 2.38 over to x equals 4, and this definite integral is giving us a negative area of the same magnitude as A2. Okay, now we can use a calculator for each of them. And instead of going over to Desmos, if you want to calculate it for yourself, just pause the video, you're welcome to, but I'll tell you what you end up getting. Take the integral from 0 to 2.38 of x cubed minus 7x squared plus 11x dx, and this is going to give you a 7.72. The integral from 2.38 to 4 of x cubed minus 7x squared plus 11x dx is going to give you a minus 5.05. So that's a good sign because we were expecting that value to be negative. So if I take both of these and add them together, I get that the integral from 0 to 4 of x cubed minus 7x squared plus 11x dx is equal to 2.67. And this value is equal to the area of A1 minus the area of A2. So the important part of this example is recognizing that when our function f of x is positive, to get that area A1, we can just use the definite integral. But if I take the definite integral when my function is negative, the definite integral is going to output the negative area as opposed to the positive area. And if I want to interpret this function, or the definite integral, in terms of areas, I'm going to take the positive area above the x-axis and subtract the area below the x-axis, which is what we ended up doing at the end. And if you want to, you can plug in a bunch of these definite integrals and just make sure that everything checks out the way that we calculated it here. So this next example also talks about the relationship between the definite integral and positive or negative area. And in this case, we're given this function f of x that's kind of abstract, and we're looking at the definite integral from 0 to 5 of f of x, and we just have to determine if it's positive, negative, or about 0 in each of the following three cases. So in this first example, notice that our function is positive for a tiny bit of the time, but most of the time it's negative. And so if you look at the area above the x-axis and the area below the x-axis, the area below the x-axis is a lot bigger than the area above. So here, the integral from 0 to 5 of f of x dx is negative because there is more area under the x-axis than above the x-axis. For part B, this kind of scenario reverses. So in this case, our function is positive over here, and then it becomes negative. And in this case, the positive area, or the area above the x-axis, is bigger than the area below the x-axis. So we get to say that here, the integral from 0 to 5 of f of x dx is positive because the area of the portion above the x-axis is greater than the area of the portion below the x-axis. And finally, in this last case, notice that the area above the x-axis is roughly equivalent to the area of the curve below the x-axis. So in this case, we get to say that the integral from 0 to 5 of f of x dx is about 0. And I won't write out the justification a third time. It's the same as before. We just look at the area above the x-axis and the area below the x-axis, and we kind of eyeball that they're about equal to one another, so they're going to cancel one another out when we calculate the definite integral. In this last section, I want to discuss how we can use the definite integral to give us the area between two different curves that we have graphed in the plane. So just to draw a picture that you should be thinking about as I give this next result, let's say that we have two functions, f of x and g of x. So f of x is the purple line that I have drawn, and g of x is this blue curve, and both of them are sitting in the plane. And we have these two different points that are going to give us the limits of integration here. And we notice that f of x is always bigger than or equal to g of x. So f of x is always above g of x over this interval from a to b that we're looking at. And I want to use the definite integral to somehow calculate this green area between the two curves. And fortunately, we actually can do this. So here's the important result that you should know and be able to apply. If we have two functions, f and g, and we have that the function f is bigger than or equal to the function g over the entire interval that we're looking at. So just like in the picture I have here, we had to notice that f of x is always above g of x over this entire interval from a to b. Then we can say the following. The area between the graphs of f of x and g of x over this interval from x equals a to x equals b is equal to the definite integral from a to b of f of x minus g of x dx. So in this case, the integrand for our definite integral is now going to be f of x minus g of x. Remember that we always subtract the function that's smaller than the other function. So because f of x is bigger than g of x minus g of x is going to be positive, and so that's going to be our integrand in this case. Okay, so for the last example for the video, let's say we have the function f of x equals 4x minus x squared, and we have the function g of x equals 1/2 x to the 3/2 for x is greater than or equal to 0. The first thing I want to do is graph these functions and then use a definite integral to estimate the area that's enclosed by the graphs of f of x and g of x. So we'll start out by using a calculator to graph the functions together. So I've gone over to Desmos, and I can take the function f of x equals 4 times x minus x squared. That's our first function, and then we have g of x is equal to 1/2 times x to the 3/2, and we end up with these two functions here. So I've taken the graph from Desmos and I've moved it over to OneNote. So here we have that f of x equals 4x minus x squared is the function in purple, and I have g of x is equal to 1/2 times x to the 3/2 is in black. Okay, and the area enclosed by the curves is colored green, and I will do that now. So the area that we're looking for is this green area between the two curves. So if I want to figure out this area, I'm going to use this information I have in the box above, and to do that, I first need to figure out what the limits of integration are going to be. So I need to find the x value of that intersection there, and the left-hand limit of integration is just going to be x equals 0. So I really just need to find where these two curves intersect on the right-hand side. And if you use your calculator, you can trace along the curve to figure out where that is, or you can go into Desmos and you can just kind of click on the point and Desmos will tell you where it is. So I'll just tell you. So this intersection point is at about x equals 3.12. So that's probably not exact, but that's a pretty good approximation. And now notice that the function f of x equals 4x minus x squared, so the purple function, is bigger than the function g of x equals 1/2 times x to the 3/2 over the interval that we're looking at. So I'm just looking at the graph of both of these functions and noticing that the purple graph is always above the black graph for the interval that we're looking at here. So now we can use the box and the result that we have in there to give us the area. So the area between the curves is equal to the integral from 0 to 3.12 of f of x, the bigger function, minus g of x, the smaller function, dx. And now I can actually plug in what those values are. So 0 to 3.12, and f of x is 4x minus x squared, and g of x is 1/2 times x to the 3/2 dx. And now I can go over to Desmos and plug this in, and we'll figure out what the definite integral is. So now in Desmos, I'm going to type in int for the integral, and we're going from 0 to 3.12, and I'm integrating the function 4x minus x squared minus 1/2 times x to the 3/2 dx, and Desmos tells me that this is 5.906. So now back in OneNote, we can finish up this problem and say that this final definite integral was equal to 5.906, where we use Desmos. And so what this tells us is that this green area between the two curves that we had graphed is in fact equal to 5.906. Okay, so that's the last example for this video, and hopefully this is enough information for you to get through your homework, everything that you need to know. And please email me, as always, if you have any questions that you're concerned with or that you want to talk about.